Hi, everybody. Good morning still, or afternoon. So I've been a finite element analyst for over a decade now. I'm actually an Altair employee still. I've worked for Altair Engineering for almost 9 years. For the past 4 years, I've been primarily focused on aerospace and defense. And for the past 2 years, I've been on site at Bowen, Philadelphia, supporting them directly, spending more or less 100% of my time there. Working with the guys in it's under Boeing Defense and Space, EES, Advanced Analysis Group. So I want to talk to you today as a finite element analyst, and less as an Altair person or a Boeing person, with some focus on aerospace. And what I really want to talk about is how the FEA community or the modeling and simulation community uses HPC, how we got started using HPC in the first place, and where we're going from my perspective. So quick overview. So first I'll talk about our requirements, what kind of jobs we run, how we're using the technology, and how that relates to HPC. Then I want to talk a little bit about how we're executing those jobs, because that's a big deal, how they're executed and running. And a quick slide on moving forward, future works. So if you brand the simulations into categories, one way that you might do that is like this. Stress is a huge part of FEA in aerospace. Stress and structural design, stress checking, looking at small displacements, looking at frequency response. All things that can be done in a small displacement world. Crash is another category. Things like impact and ditching. Basically anytime one thing is crashing into another, I think of that as crash analysis. There's thermal and multiphysics, computational fluid dynamics. If you're into aerospace, the aero group typically likes to run in the CFD arena. And then there's optimization. And I think we'll talk one slide about the first two and the last bullet point on here. And we'll take a closer look at that. So how do we use stress? How do we use FEA for stress? Well, let's just put all these animations on here. So typically the process looks like this. While they're working with the CAD group all the time, represented on the left-hand side, the aero group, or the guys that run CFD, will produce loads for the aircraft, usually at the system level, but occasionally at a component level. And down at the bottom, you can see global and local, but I think of global and system level as the same thing, and local and component level is the same thing. So I would almost use those interchangeably in this format. So the aero group gives us loads from their CFD analysis, and then we take those loads and then we apply those to a large system level model of the aircraft or the rotorcraft or whatever the case may be. And from that we produce base stresses, base displacements. We can extract loads from that, frequency response, among a series of other types of analyses that we don't need to go into. Also, more detailed component level analyses are performed using either a finer mesh or a variety of hand calculations and simulation to get to take a finer look at what's going on in that area. And then you have down on the bottom right, portion of the slide represents more non-standard detailed FEM. Occasionally they'll take a piece of the model out. Sometimes they'll call it a breakout model. Sometime depending on what arena you're in. And it's on models like this that we perform things like optimization, nonlinear analysis, vulnerability studies. The list could go on. I could probably name a dozen different types of analyses. So a quick look at stress. We look at the way we use FEA for stress. Crash, I've organized this a little bit differently, just 3 pictures. So 3 of the main arenas that we use FEA for crash is, one of them is ditching, whether that's, again, it's usually full aircraft ditching. It's either aircraft, rotorcraft, also spacecraft. Anytime anything can crash, you'll find a group that's probably running some type of ditching analysis on it. Bird strike is absolutely huge. There's growing requirements for bird strike in both the commercial and the defense arena. Both Philly and Everett have bird strike centers of excellence that are pretty much running bird strike nonstop. And then you have projectile analysis. That's also another huge area. Anytime something that is very fast is hitting something that is moving very slow or not moving at all, and that includes things like hypersonic impact. Anything from, you know, a bullet hitting a helmet, a new composite helmet, to a piece of space debris hitting an astronaut suit I've seen. And then a quick note on optimization. So a lot of times if you see an FEA guy present optimization, it'll be a fairly complex optimization. So I wanted to go a different way and do something a little bit more basic, like this bracket. And the reason I like this one is because it's so different, is because the weight savings, typically what you look for in aircraft optimization, probably the vast majority of the time you're looking for weight savings, but you could also look for stiffening. You know, if the project requirement change, you might need a stiffened component, and you might not be worried about weight in that case. In most cases, it is weight. But I like this example because instead of optimizing one part and cutting many pounds out of that part, they're optimizing many different parts and cutting just a fraction of a pound out of each one of them. So without saying too much more about this particular case study, there was over 100 of these brackets that needed to be optimized, and somebody figured out if they could just take a couple ounces out of each one, it would be a major cost savings. So anyway, that's really briefly how we use FEA. So if you take those categories and you rebrand them under solution options, so then we have to find a program or an application that can actually solve these problems we've set up, right? And we sometimes call those solutions, although the solution for FEA is really the problem for HPC, right? But so if you rebrand our solution options, I like to think of them as in 3 gross categories. And you see linear analysis, iterative or convergence analysis, or explicit or time-dependent analysis. They have many different names depending on who you talk to. So the obvious, I've listed one single pro and con for each one of them. And linear analysis, the obvious pro is they carry the smallest overhead. Okay, they're typically very fast. As you can kind of see over on the right, they're more memory intensive than anything. But they have a limited scope. So if your displacements start getting large or you start to sense nonlinear behavior, you have to move to an iterative solution. You get a wider scope at a bargain for time. But occasionally you have a failure, and that's kind of the nature of the beast. Failing everything else, you can run a time-dependent analysis. With it, they have a nearly unlimited scope. You can do almost anything with it. And but the run times can get really quickly. I mean, you can run jobs that run for minutes or a month if you want. And I've seen jobs run for a month purposely. So my scale on the right, memory and processor. So when I think of, and again, these are generalities, but when I think of the constraining resource for a linear analysis, I think memory. And when I think of the constraining resource for an explicit analysis, I think of processors. So like your standard linear analysis, and these different solution options have completely different coding behind them. So the way that they're coded up and actually executed and carried out is completely different. And typically with a linear analysis, they'll want to, the core of the code will rely around inverting a giant matrix. And if that matrix can all be in core, so to speak, it's done very quickly. But if it's got to be written to disk, then you're in deep water because it's going to take a lot longer. And then with the explicit codes, You don't typically need this, you don't have that huge memory requirement, but you can increase your speed exponentially, well, not exponentially, it's kind of inversely linear. You can increase your speed by using more processors. You can throw more processors at it. And they're typically more scalable than a linear analysis. So that's the way I think memory and processors. So taking that and moving on to job execution. So kind of switch gears for a minute. Let's talk about job submission interfacing. So how do we actually submit our jobs now? Now that once we know what we want to do, once we have our model built and we want to hit go. It's really nice if you could do a pre-processor launch, and what that means is there's some other application that you're using to set up your model, and it would be really nice for everything to be a black box and push a button and it runs in the background and you never see it run and you get your answer and you look at it. That works really well if you're working with a smaller model and it's local or a test model, but once you have to go into the HPC, or once your computer can't handle that and you have to go to HPC, that really isn't an option anymore. So you move up to prompt and script, right? So typically what guys do is they'll tunnel into the machine, the cluster, or the HPC unit that has the software installed on it, and they'll either write a script or do a direct execution. And not really the problem, but the thing I noticed about that as someone who runs multiple different solutions is that the solution has to be repeated each time, every time you use a new piece of code, and that can carry more and more overhead. You have to designate someone to control each one. Enterprise management interface is one level up from that. It's actually kind of getting closer to the black box from the preprocessor launch. So you have the idea is you have a single interface for all your solutions. So you have one single piece of software that's doing each of the prompt and script solution in the background. I have a picture off to the right that kind of depicts what a typical interface might look like. So the idea there is the user gets his job ready, drops it in a folder, hits go, and the computer takes care of the rest. And if you have to, so if you're somebody that deals with many different types of solutions, you don't have to learn 4 or 5 different ways to submit the job. You just learn one. If you're a guy that only runs one different type of solution, then it's a harder differentiation between those second and third bullet points. Then on a different level, once the job is running or deciding where the job runs to, we can talk about resource management. At the user supervision level, so most companies today have some type of software that controls what their HPC units are doing. I'd be hard pressed to come up with somebody that doesn't have some type of software. But what still happens today is there's certain clusters set up for certain solutions. So you might have a group that has access to 3 different machines, and you can run A on machine A, and you can run this type of solution on machine B, but you can't really cross-pollinate. And it directly just leads back to guys, kind of talking over the cube. Hey, can you shut this job down? I got to run this job. And it's not always the HPC unit's fault. It might have to do with, or fault is a bad word, but it might have to do with licensing or some other aspect, right? But at the enterprise level, so I'm skipping ahead here. So at the user supervision level, you're still, if you got to run B on B, but there's licenses or resources available on A, you can't really get to them because you have to run on B. But at the enterprise level, you can overcome that. Enterprise HPC or grid and cycle harvesting, and possibly even cloud. I mean, can we take our own software and put it on someone else's HPC? And I haven't mentioned up to now, bad time to mention it, but when we run our jobs, I mean, this has been fascinating for me listening to the talks. The limited number of talks I've been able to hear today, about the number of cores that get the number of cores that get used in some of these jobs and the amount of data that's going back and forth. Our stuff must seem like small potatoes, we run many jobs, but the jobs themselves don't get that big. I mean, I personally might run, 100 cores. We could run our job on 4 cores if it was a small enough job. I've never seen something run on 1,000 cores in our arena. So, but when you talk about data transfer, that is very near and dear to me, because moving forward, I see room for some improvement. And some companies are already doing this. Some are kind of late to the game, but remote post-processing is one of the hugest areas that I see in the next decade. It's critical, and also for visualization. So what I mean is, we put, and I think somebody else was talking about this morning. So there was, you put a little bit of data in, and you get a huge amount of data out. And it's annoying as the end user to upload a couple of megabytes and wait a couple hours and then have to download close to a terabyte of information and then juggle that and either compress it or place it somewhere else, and now you're pulling it in and then you're pushing it out somewhere. So that's 2 transfers, and you don't really shouldn't have to do that. And then you have to consider about storage of the substantiated results. So you might get out of 10 results, you might need to save 5 of them. You might need to record that, document it. It's data that can't be destroyed, so it has to be placed somewhere. With remote post-processing, not only can you avoid that download because you're doing the post-processing on the server, but you can also visualize it. So I say a lot of times we're doing hours of file transfer for minutes of engineering, right? I have to wait an hour for my files to download so I can look at all the data in a concise format and look at it for 5 minutes and make a decision and then go to the next iteration. That's ridiculous. So remote post-processing is something that we're really looking at really closely. And then visualization is kind of one step beyond that, is where the image is getting pushed. I think that's pretty self-explanatory. The image is getting pushed across the server directly to our screen. So it's very interesting to us. The other thing is HPC optimized for the solution. So a lot of times when the HPC system is set up, it will be optimized or certified or whatever for the system that it's on. And maybe for one of the solutions that the organization or enterprise is using, but not all of them. Or you might get a solution comes in the door afterwards, and the HPC system or the solution never get hooked up properly. I see a lot of cases where it's not even performed at all. And this leads, as you see there, I've seen cases where, and they don't happen all the time, but in my opinion, it should never happen, where a high-end PC is actually outperforming a 5-year-old system, a 3-year-old system in some cases. So we want to make sure, and that's something more on the organization level, where we have to make sure that we're doing that correctly, and that we understand the HPC needs and they understand our solution needs, and we can get that hooked up properly. Just a quick plug for Display Manager. I'm an Altair person. This is an Altair product, but I recently got turned on to Display Manager, and when I guess when I started writing this, I didn't really realize that Display Manager was as evolved as it was. So we actually are looking at implementing this on site right now to solve our visualization problem. So maybe it's solved. Display Manager is it fixes the problem that I was explaining about remote visualization, essentially. I don't know if I want to go into it any further. Just a quick summary, really obviously, we as a simulation community, we tend to build jobs based on the availability of the resource. So, if the servers get faster tomorrow, we'll build bigger jobs. I think that's just kind of natural. I guess we're doing what we're supposed to be doing. I always can't wait to see what the next system's going to look like, because we're always pushing the limits of the software and the hardware. And job execution is moving towards the enterprise level, which that's a clear trend, and I'm happy about that. I guess is what I want to say. So that's really all I have, short and sweet. Is there any questions?